So, Pavel, the most important person, we're so happy to have you here from Poland, from Warsaw. So, Pavel was a summer student here at CERN back in 2012.
Exactly.
And now he is a scientist, he's an entrepreneur, and also a consultant. And he works mainly in IT, so AI, and also quantum computing. And he's also created a foundation and is also a member of OQI, which is the Open Quantum Initiative, which is something which has been started here at CERN. And I believe you'll be back
Yes,
for that event.
hopefully in October.
Great. Now, not only that, Pavel happened to be at CERN when the Higgs boson was discovered, which was a very exciting time for you. And his football team also won the CERN World Cup. Yeah, the CERN Football World Cup. So many achievements.
Exactly.
So on that note, what I'd like to do is hand the floor over to Pavel. Thanks again for everybody. Hello, come on in. We're about to get going. So please take it away.
Thank you. So, hello, everyone. It's really great and exciting to be here after 13 years, indeed. So I believe that some of you are also summer students or used to be summer students. So you can imagine how one may feel when you come back to CERN after so many years. And I would like to thank Rachel, Simona, and the whole alumni network for inviting me and giving this opportunity to tell you about my experience, my journey, my current activities. So indeed, as I was introduced, I'm currently the chairperson of the board of QWORD, which is an international organization aiming to contribute to the development of open global ecosystem in quantum technologies and democratizing access to education in quantum technologies. And I'm also CEO and the founder of Fundacja Quantum AI, or in English is Quantum AI Foundation. It's a non-profit organization that I founded a few years ago. So I will later also tell you more about these two organizations. But going back to actually before the CERN area, because I think it's good to also tell you more about my background and my experience before CERN, because I believe it can also give you a good context. I was also fascinated. I was always fascinated by science, especially math and physics. Later, computer science, but actually, I got interested in computer science only when I started studying at the University of Warsaw. So I also achieved some good results in some mathematical and Olympiads and competitions. So I started studies at the University of Warsaw, and these were double degree studies in both math and computer science. So I graduated in math in 2009 and computer science in 2010. And then I started my PhD in computer science at the University of Warsaw. So as you can see, unfortunately, after my high school, I had to make a difficult decision. And among all the things that were very interesting for me, like math, physics, and later also computer science, I had to decide what exactly I would like to focus on, because, you know, you can be passionate and interested in many things, but it's always good to focus on one or two things at most. So that's why I later became a mathematician, computer scientist. And then when I started my PhD studies, they were in computer science. And they were mainly in artificial intelligence. And it was it's very interesting because, you know, I started my PhD studies in 2009, so already 16 years ago. And the world was quite different. So the AI was not that popular at that time. And I can tell you that when I was recruited for the PhD studies, I got a question, why would you like to do PhD in AI? Because just about 20, 30 years ago, we had AI winter. So it doesn't seem that AI may develop in the future, right? So maybe it's better to focus on something else. But I insisted on doing PhD in AI, indeed, and it turned out that it was a good decision. So formally, the title of my PhD was Meta-heuristics in the optimization of complex processes. So I will tell you more about it later. So in particular, I started working on building mathematical models of complex processes like road traffic in cities. So I developed a software for simulating traffic on large scale, like the scale of the urban area in Warsaw. So it's a map of Warsaw taken from the OpenStreetMap, and these colorful dots are just different cars, and their colors correspond to the current speed. So there was a microscopic agent-based model in which I was able to simulate the realistic traffic in Warsaw. So actually, it was, I can say that it's also physics, right? Modeling the real-world phenomena. So I developed this tool in 2009, and later started applying it to optimize to optimize traffic signal settings, and later to solve some other transportation problems. And I also started doing some internships at the end of my master's studies and later during my PhD studies. So first I was a software engineering intern at Microsoft in Redmond in the US. Later I was also an intern at Google. And during my internship at Google, I attended a lecture about CERN. So it was 2011. I do not remember who exactly from CERN was at Google at that time, but there was a very nice lecture. And later I decided to apply for an internship or summer student program at CERN in 2012. One of interesting and maybe a bit funny reasons was also that in 2011 I heard about this famous opera faster than light neutrino anomaly. Maybe you also remember that or heard about it. So later, of course, it was explained, and I became very curious, right? So I thought that, okay, so something interesting is going on in CERN right now. So maybe it's good to go there for an internship. So I applied to be a summer student in 2012, and I was an intern in the BIMS department, in the BIM loss section. And formally, so this is a photo from my ID card. I took the photo just before I had to leave my ID card at CERN. So I was working on a software tool for analyzing data from detectors monitoring beam losses. So that was my goal, and I worked in on the Prevesen site. So it was July to September 2012, and I was very lucky, very fortunate, because just a few days after my arrival, the discovery of the Higgs boson was announced. Right, so it's hard to imagine a better time to be at CERN. So you can imagine that of course there was a press conference. There were many journalists. There were many scientists coming to CERN. So everyone was talking about it. So it was a really great time to be there. And as summer students, we all felt that we are in the center of the world, in the center of the science, at least the scientific world, where the most important things in science are going on. So that was July 2012. And from my experience, so my memories are great. So for me, and after 13 years, I can tell that it was one of the best summers in my life, definitely. So of course, I learned a lot. I met many great people. So here are some photos from our trips to the Recollet, Aguilé du Midi. It's at Mont Blanc. So we went to Chamonix, and I tried to take as many opportunities as I had. There were many events happening at CERN. There were also many events and interesting places to visit in Switzerland and France. So of course, we're traveling together with other summer students to explore, because for most of that was the first time here in this geographical area. And there were also some other interesting events. So Rachel already told about it, that together with my colleagues, they were mainly from Poland. We won the CERN 2012 World Cup in football. There was a competition at the football pitch. There was a football pitch in Saint-Genis-Pouilly. Maybe you know it. It's not far from this the hotel in Saint-Genis-Pouilly. So yeah, there were teams of six people. I think about 8 teams. I remember that. So that was a team of Poland. Actually, there were 4 guys from Poland. 2 of them, Marcin and Wojtek, were physicists, and they were also very good football players. I remember that they played in the first team of CERN in general. There was also one guy originally from Portugal, Ricardo, but when he was at CERN, he was also a student in Poland, in Lublin, and his girlfriend was from Poland. She later became his wife. So we said that, okay, so he is already half Polish, so we can invite him to the team. And there was also one of our neighbors from Slovakia. He was the only person from Slovakia, so we said that, okay, he's our neighbor, so we can also invite him to the team. So that was a great experience. I remember there was also a table tennis competition in Meran. There was a club, and I was in top 16 or something like that. That was a good time. So I later asked ChatGPT recently to generate an anime photo of this picture with the cup. It seems funny. And what happened later? So I was in CERN for 3 months in 2012. And later, when I came back to Poland, so actually there were some discussions about continuing my collaboration with CERN. There were some ideas to do a project on Monte Carlo simulations because it was also related to my PhD project. But unfortunately, it didn't happen, and I also started focusing on some other things. So in 2016, so anyway, first of all, I continued my main research on optimizing traffic signal control using AI. So that was the primary area of my research interests at that time. So in 2016, I started an independent research group that is called TensorCell, because we obtained some interesting results that were published at the NeurIPS conference in 2016. And so I also received many applications from people willing to join my group and doing this research together with me. That's why I also wanted to focus on this specific area. And we explore some interesting new research directions, like in general, analyzing complex systems, complex processes, and the complexity science, approximating traffic simulations, or in general, simulations of complex processes using machine learning models as surrogate models. We propose some new architectures of sparse graph neural networks. We started applying reinforcement learning to optimize complex processes like to traffic signal control. Later, I come up with an idea to adapt these techniques to optimize cancer treatment using radiotherapy. I also started working on modeling traffic, including connected autonomous vehicles. So these are some different research directions that I was exploring at that time between 2012 to 2017, more or less. In the meanwhile, I also did a research internship at IBM Research in Dublin, Ireland, in the Smarter Urban Dynamics team, and I was also working on traffic prediction using machine learning. So already then, more than 10 years ago, machine learning was already applied to different domains, of course. So thanks to my knowledge, skills, and experience, it turned out that people and different companies started contacting me and asking for help in different things they were working on. And I generally enjoy helping people. So usually I wanted to help somehow. So I started serving as an advisor, consultant for different companies, mainly startups. In particular, also co-founded two startups. One of them was Let Me AI, focusing on applying AI for e-commerce. So we wanted to build something like a virtual shopping assistant, helping people do online shopping on the internet. And another one was Broomy Technologies, where we applied AI for managing fleets of van pooling services that could be ordered using mobile application. So I was not the main founder there, but I was a significant person in both these startups. So later in 2017, I gave an interview in Polish radio, where I was talking about AI applied to optimize road traffic. And I didn't expect that this would be the beginning of my journey in the quantum technologies field. Because just after the interview, I was contacted by the CEO of a new startup that was called Bohr Technologies, a very nice name. And they wanted to apply quantum computing to solve routing problems in logistics, right? So these problems are NP hard, but I learned that there had already been quantum approaches to tackle them. So I started learning about quantum computing. And as we currently have the International Year of Quantum Science and Technologies, it's officially announced by the United Nations. Then I also would like to tell you a bit more about quantum computing, because I believe that for some of you, this could be a new topic. So some of you may ask what exactly the quantum computing is. So the simple, probably too simple answer is that these are computations according to the laws of quantum mechanics. But of course, the real answer is much more sophisticated. And how everything started. So Richard Feynman in 1960 said that there's nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. In fact, there can be certain advantages. So if you follow the history of computer science, you probably know that in 1940s, 50s, the computer elements were much, much bigger than they are nowadays, and even when they were in 1960s. And people already observed that there is a progress, right? That the computing element can be made much smaller. And there was even an observation that was formulated as the famous Gordon-Moore's law, that the number of transistors in a dense integrated circuit doubles about every 2 years. And this prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for R&D. But about 10 years ago, Gordon Moore himself said, I see Moore's law dying here in the next decade or so. And Intel, the company working on processors, also observed that the pace of advancement has slowed. So now the doubling is not once per 2 years, but rather once per 2.5 years. And actually at the beginning, when the Moore's law was formulated, it was even once per 1.5 years, more or less. But of course, this trend will continue for some time. But the question is if this trend could continue forever. So let's assume that this trend can continue. So it will turn out that in about 2035, 2040, a size of a single transistor should be of a size of a single atom. And in such a small scale, the transistors cannot, that we know, as we know them today, they cannot operate in such a small scale due to the quantum mechanical laws, of course. And actually, even much earlier, we already see that there are already difficulties in pushing the Gordon-Moore's law further and to increasing the density of the transistors in the integrated circuits. So, but of course, we can scale in different dimensions, right? So we can add more memory in general. We can add more CPU. We can do parallel computing and so on. But it's also a natural question to ask how we could perform computation in such a small scale of atoms, right? And again, Feynman, who is considered as one of the fathers of quantum computing, said that we can, in principle, make a computing device in which the numbers are represented by a row of atoms with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function. The ones move around, the zeros move around. And finally, along a particular bench of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller. Nothing could be more elegant. No losses, no uncertainties, no averaging. But can we do it? So as I'm now talking about quantum computing, you can already guess that, yes, we can already build some initial quantum processors. So here you can see a photo of the Google's quantum processing unit that is called Bristlecone. And here on the right, you can see a cartoon of the device with each X representing a qubit with nearest neighbor connectivity. So I've already mentioned the magic word qubit. So what does it mean? And what's the difference between classical computers and quantum computers? So as you know, in classical computers, we have bits and classical gates, right? So in bits, we can store true or false, 0 or 1. And we have classical gates like AND or NOT that can take some bits as an input, and they can produce an output, another bit that can serve as an input to some other classical gates. And this is how classical computing works, more or less. But in case of quantum computers, we have quantum bits or qubits in short, and we have quantum gates. So what's the difference? So I've already told you that in case of a bit, a state of a bit is may have a value 0 or 1. So mathematically, it's something relatively simple. It can be an element from the set 0, 1. But in case of a qubit, a state may be in a superposition of states 0 and 1. So mathematically, it can be a unitary vector of the two-dimensional Hilbert space over complex numbers. So you can already see that even mathematically, it's much more complicated. So I will not go into details here because the quantum computing domain deserves separate lectures, of course. But I will tell you about some other differences and why it is important and some applications of quantum computing before I move forward. So in case of classical computers, the state is determined. So we can know exactly whether the state is 0 or 1, and it can be changed from 0 to 1 and vice versa using classical gates. But in case of quantum computers, to get value 0 or 1, we have to do a measurement which breaks superposition. And probability of getting 0 or 1 after these measurements depends on the qubit, which is the unitary vector in a two-dimensional Hilbert space over complex numbers. And our quantum gates can modify the qubits, the states of the qubits, and they can modify the probabilities of getting 0 and 1 as a consequence. So why it is important? So on n bits in classical computers, we can process only one n-bit number at the same time. in case of quantum computers, using n qubits, we can, in theory, process all possible 2 to the power of n bit numbers at the same time, just by changing the probabilities of obtaining different results after the measurement. So there are some probabilities in case of quantum computing. So another difference, in case of classical computers, the results are deterministic, and randomness is actually a pseudo-randomness. So we have generators of pseudo numbers. So this randomness can be replicated if we want. But in case of quantum computers, we may have, let's say, real randomness, whatever it means, because you know, there are different interpretations of quantum mechanics. So we cannot say that we fully understand what the randomness is in our real world. And thanks to that, we can easily sample from probability distributions that are difficult for classical computers. So for example, there is a Boltzmann distribution, which occurs in machine learning, that is quite difficult for classical computers, but should be easier to sample from for quantum computers. So what are the applications of quantum computers? Breaking some classical cryptography algorithms, for example, maybe you heard about the Shor's algorithm that can factorize large numbers in polynomial time, and many contemporary cryptography algorithms, encryption mechanisms are based on the assumption that the factorization problem is difficult. So it's probably difficult for classical computers. However, it hasn't been formally proven mathematically. But we already know that this problem is relatively easy for quantum computers. So that's why there is a very important area of research that is called post-quantum cryptography. We can also apply quantum computers to solve some combinatorial optimization problems that frequently occur in different domains like finance, logistics, also AI, machine learning. So the whole machine learning domain is all about optimization. Even when we train neural networks, we want to find the values of the weights of connections between neurons that would minimize the loss function on our training set. We can also sample from difficult distributions. I've already told you about Boltzmann distributions, so we can create quantum random number generators, and it's already happening. We can simulate some quantum processes which can help us to discovering new materials, new drugs. We can search in unstructured databases using Grover's algorithm. We can generate art. I've already heard about music or some pictures generated with the help of quantum computing. It's also important to emphasize that there could be some other applications of quantum technologies. So quantum computing is only one thing, but there's also quantum sensing, quantum metrology, quantum communication, quantum key distribution, right? Quantum number, random number generation. So, and actually quantum computing itself is probably even not considered as the closest one to real world applications now. So probably quantum metrology or quantum sensing could be closer to real practical, real world applications. Okay, I've already told it, but it's important to emphasize it once again. This year, 2025, is announced as the International Year of Quantum Science and Technology to recognize 100 years since the initial development of quantum mechanics. And you can check the website, official website of this International Year of Quantum, where there are many different events related to quantum technologies happening all over the world. Some of them are on-site, some of them are online. If you were here at CERN in July, or if you follow the news, you also probably heard about an interesting discovery here. I know that it was already announced in July. So there was a demonstration of first antimatter quantum bit that paves the way for substantially improved tests of nature's fundamental symmetries. Like we can read that this achievement marks the first demonstration of an antimatter quantum bit or qubit and paves the way for substantially improved comparisons between the behavior of matter or antimatter. I'm not sure if it will lead to some, let's say, further discoveries like discovering new ways of building quantum computers or physical quantum bits, because there are already many different approaches based on superconducting, ion traps, photonics, and so on. So we'll see if someone will try to build quantum computers based on antimatter, but it seems to be a very important discovery, and it was done here at CERN, of course. Yes, so coming back to my research, I see some of my colleagues from the Open Quantum Institute as well. So I can already also tell that indeed I'm also collaborating with OQI. And I'm leading a project titled Quantum Optimization Solution to Optimize Last Mile Food Delivery, minimizing waste and costs. It is related to several SDGs, the so-called Sustainable Development Goals. So we aim to minimize the food waste, to reduce the hunger, to reduce the negative impact of the climate change, or reduce the climate change, actually. Right, and indeed we test different quantum approaches, starting from quantum annealing, which is our main focus and main area of research, going through some other quantum approaches like QAOA, quantum approximate optimization algorithm, or variation quantum eigensolvers, or some combinations of quantum computing and machine learning. So we are also considering such approaches. So it is an international research team. So I'm from Poland, and there's also one more person from Poland, but we also have team members from the US, from Netherlands, from India, and Morocco, and maybe some new team members will formally join us soon as well. So currently there's a white paper published by OQI on the OQI's website where you can read more about this use case, and there are also many other or some other interesting use cases supported by OQI. And I also support another interesting research project I wanted to tell you about, because in general, quantum computing is considered as a one-way computing. So we initialize our initial qubits, then we apply some quantum gates, then we do the measurement, and then we can interpret the results. But there is also another very interesting idea that as a Quantum AI Foundation, we support or try to support. And there is an idea to build the so-called two-way quantum computers, in which the state preparation on the other side of a quantum computer could be similar to the first side. So actually some, we can already prove that in theory, this could lead to solving some NP problems in polynomial time. We do not believe that it will happen, but we've already carried out some experiments demonstrating that even if it's not possible in practice, then there might be some interesting advantages, perhaps. So it's still a relatively early stage of research, but the idea seems to be very interesting, and we support it. We recently also submitted this idea to the X Prize quantum application competition. Maybe you also heard about the X Prize. Okay, so coming back to my journey, because I also wanted to tell you at the end about some more, let's say, educational projects that I'm currently leading. So I've told you that I started learning quantum computing at some point, so it was about 2017. And it's always good to learn together, right? And also learn from other people and with other people to learn from the others. So I created a Facebook group that is named Quantum AI. You can still find it on Facebook. Currently, there are more than 9,000 members. And in 2017, I just started sharing news and learning about quantum computing with other people. And more and more people started joining, and now there are more than 9,000 members. And one of the first most active group members was Peter Morgan from London. So when I attended one conference in London, I decided to contact him and meet with him in London, and he invited me to attend a London quantum computing meetup. It was a great event. There was an invited speaker from D-Wave. It's a company from Canada working on quantum annealing hardware and algorithms. So I really enjoyed that event. So I decided to start organizing similar events in Warsaw, in Poland. So I launched the Warsaw Quantum Computing Group in 2018 to commemorate the 100th anniversary of regaining independence by Poland. So of course I needed a legal entity to process contracts, accept donations, sponsorship, and so on. So that's why I founded a non-profit organization that's called Quantum AI Foundation. And I also started creating some other profiles on social media. So there was a good visibility of these activities. And that's why I got interest from quantum researchers from other countries. So it turned out that when you are active on social media, some interesting and sometimes unexpected things may happen. So this is just a website of this Warsaw Quantum Computing Group meetup. You can check it and watch the recordings of our previous episodes. We've organized more than 60 events so far. And thanks to these activities, in 2019, I was contacted by Dr. Abuzar Karilmas from the University of Latvia, who developed an introductory course on quantum computing and started traveling to different cities in Europe, especially Central and Eastern Europe, to teach quantum computing based on his materials. And this was still the time when quantum computing was not that popular yet, and there were not many educational materials available. So it was 2019. And Abuzar, with his colleagues from Latvia, visited several cities in different countries in Europe. So this initiative was called Q-Drive. So we are laughing that perhaps you can try to optimize their logistics using quantum computers as well. As you can see, the number of cities was not that large for quantum computers. And during these meetings, some discussions emerged to start an international collaboration in developing more educational materials and organizing educational events. And this is how QWORD started in 2019. So what is QWORD at the end? Because I also told you that currently I'm the chairperson of the board of this organization. It is a global network of individuals, groups, and communities collaborating on education implementation of quantum technologies and research activities. So in simple words, we work together internationally to develop educational materials on quantum computing. And based on these materials, we organize educational events like workshops, meetups, lectures for our local communities in different countries. We have 3 departments: Q Education department responsible for developing these open source materials. This is important. All our materials are open source, available under the Apache license. So if you want, you can also use them for organizing your educational activities. We have Q Cousins department, so we collaborate globally, but we also have our local operational groups in different countries, in different cities. So they are called Q Cousins or Quantum Cousins. And we have a Q Research department in which we do research, and currently we have one main project that is called Q Intern. So I will also tell more about Q Intern soon. So currently QWORD is one of the largest quantum communities worldwide. So on our Discord server, we have more than 3,500 people. We have 36 Q Cousins in 36 countries. We've organized more than 200 workshops. We've handed out more than 10,000 certificates. I think that now it's already more than 15,000 certificates. We have 5 default flagship quantum computing courses. Q Prep is a preparatory course. Q Bronze is our introductory level. So in Q Prep, we just teach the basics of math like linear algebra or programming in Python. In Q Bronze, we already teach the basics of quantum computing. We introduce the quantum phenomena like superposition, entanglement, and so on. In Q Silver, we focus on the Shor's algorithm and quantum Fourier transform. In Q Nickel, we focus on oracular algorithms like Deutsch algorithm or Grover's algorithm. Q Zinc is about quantum error correction. There are also some self-study models on quantum annealing, topological quantum computers, and I remember what I forgot what's the third one. Oh, sorry, the third one is the self-study is also on quantum error correction. We also already have a quantum semester that's called Q Class. So we organize online quantum semester where we offer all these courses and some other additional lectures over several months. And after all these workshops or events, people can get the certificates if they want, of course, and if they pass our final tests, of course. So after all these workshops, we have our standardized tests, and people can take this test, and if the results are good enough, like they need to obtain at least 70% of the points, we can give them a certificate. We also have a Q Intern program. It is a very interesting program. I think it's quite unique worldwide. I will tell more about it now. So it's a program of, actually it's a matchmaking for online research internships in quantum technologies. So the idea is that first, researchers from all over the world apply and propose their ideas for research projects. And then students from all over the world can apply and select their preferred projects. And then we try to match them. Of course, the final decision belongs to the mentors, to people who submitted the projects. So there is a recruitment phase. And then there is finally the Q Intern program where they form a team, the teams that were formed work together, being guided by the senior researchers who proposed the project. And finally, there is something like a demo day, a mini workshop for presenting the outcomes of the project. So these are just examples, 3 examples of the projects that we had this year. This year we had about 17 projects as far as I remember. And every year we receive about 400 applications from the students from all over the world. This year it was close to 600 already. So there's a huge interest in this Q-Intern program because, as I said, I think this is quite unique worldwide. I haven't heard about any other similar program for research internships in quantum technologies. And finally, the Q-Cousins department that I also lead. So we have these local operational groups in different countries. So currently we have 36 Q-Cousins. So yeah, we want to engage every country at the end. We want to cooperate, work together to develop educational materials, but act locally to offer these workshops to our local communities. Of course, we are open, we promote diversity, and we all like also to engage younger generation, even starting from high schools. We even sometimes offer dedicated workshops for high school students. So I'm also the coordinator of Q Poland, which was one of the 5 founding members of QWorld. So just some information about Q Poland if you are interested. And Fundacja Quantum AI, so this nonprofit organization that I founded, is also a legal entity behind Q Poland. So it formally supports all the events that we organize. We also organize some other events, not only workshops and meetups, but also hackathons. This year there will be a 5th edition of our Q Poland Global Quantum Hackathon. So it will be an online hackathon. I know that close to the date, there will be also an on-site hackathon happening here at CERN. So it seems that this will be the first time when I will be in a superposition, because I will be a mentor in this on-site hackathon, and also I will be launching an online hackathon for the global community. But luckily, this online hackathon will last longer for 8 days. We also organize a conference on quantum machine learning. So this year there was already the 5th edition of this quantum machine learning conference. So it's fully online. We release a monthly newsletter, Q Poland newsletter. If you want to stay up to date with the curated news from the quantum world, we invite you to subscribe. We also release AI newsletter that's called Warsaw AI News. And in this case, the newsletter is weekly because there are so many things in AI happening every week that it's difficult to stay up to date. And every week we send about 60 to 80 news from the AI world. And we also organize a Warsaw AI meetup. This is an on-site meetup in Warsaw for AI practitioners, AI specialists. So if you are in Warsaw, maybe you'll have opportunity to attend one of our events.